Okay, so good morning everyone. So yesterday on Wednesday, we started talking about quadrature. So quadrature is just numerical integration. Like suppose you have integrals you cannot compute by antiderivatives, then the only way is to compute using numerical quadrature formulas. And a quadrature formula is just a formula that approximates the integrals of a function from a to b. And I take a form like this, okay? So w1 up to wm are called the weights, okay? And x1, x2, xm are called the quadrature points, okay? And we discussed a class of Newton-Cotes rules. So with only one interval, yeah. So now the idea is to just approximate f by the interpolation polynomials of f, and then the integrals of f is approximated by the integral of the polynomials, okay. Then the weights is just the integral of the Lagrangian, okay. And then by choosing m from 1 to 3, so on, then you have a better and better approximation for the integrals, okay? So we did some example. We did like m equals 0, m equals 1, then it's just midpoint rules. Midpoint rules. So again, here everything is just one interval, so just fix one interval. Yeah, one interval, very fast intervals from A to B. And the midpoint rules, you just take the value of the midpoint, you multiply with the width of the intervals. The trapezoidal rules, okay, is you just take the trapezium, like spanned by AB, FA, FB, and if you use the formula for Newton-Cotes rules, then first you just have to compute the Lagrangian and then compute the weights by the Lagrangian integrals from A to B of the Lagrangian. And then, for m equal 2, x1 equal a, x2 equal b, then you recover the trapezoidal rule. So we discussed it last time, yeah? And then you can increase m to be 3. Yeah, so 3, then essentially you approximate f by a quadratic, yeah, quadratic that go through 3 points, A, B, and the midpoint. And then by evaluate the weight of the Lagrangian, you can come up with this formula, and we call it the Simpson rules. So then after the first person who discovered that. Okay, so Simpson rules can be related to midpoint or trapezoidal rules by this relation. Okay? You just look at this formula, and the Simpson rules is just 2/3 the midpoint plus 1/3 the trapezoidal rules. And we also discussed about the degree of precision. So degree of precision is, first you define the errors. So what is the error? So the errors is the difference between exact integrals and the quadrature applied to that function, okay? And you can see that the errors, here we don't have absolute values, so that's why the errors plus the quadrature equal the exact integrals. And if the errors equal 0 for function 1, function x, x squared, xr, but if you increase to x to the r plus 1, then the error is not 0. Then we say that the quadrature has degree of precision r. Okay? So now the consequence is, if I take a polynomial of degree r, then what is the errors? So if I take a polynomial of degree r, and the degree of precision is r, then what is the errors? 0, yeah? Because, you just take the linear combination. So suppose I have a polynomial like a0, a1x plus a2x squared arxr, right? Then, so this one is P. Then the errors of P is just a0 plus a1 e of x, yeah, because the errors is linear. So you can, question? You can do this, yeah. So you can distribute the errors into each term because it's linear, because it's just a difference between integral and a sum. So it's linear. So you can prove this. And you see, because so this one is just E1, yeah. So therefore, this one just equals 0, 0 here, 0, 0. So therefore, the whole thing just equals 0. Okay? So that is the statement here. So if f, so because EF is linear, yeah, so it means that if you have a polynomial of degree r or less, yeah, then the integral is exact. So it means that the error is equal to 0. Yeah. But if you replace by polynomial of degree r plus 1, then the error is not 0 anymore. Okay, so we did some example for degree of precision already. And now, you know, by direct calculation, you can show that the midpoint and the trapezoidal rules have degree of precision 1. Okay? And we did an example of a Simpson rules. We didn't do the example for general Simpson rules, but we did an example for Simpson rules from -1 to 1. And you see that the degree of precision will be equal to 3. Okay? And in general, the theorem says that suppose you have m point interpolatory quadrature rules, then the degree of precision will be at least m minus 1. Okay? And if m is odd and the point symmetric with respect to the midpoint, then the degree of precision will be m. So we are going to prove it quickly. So how do we prove it? So now what I want to show is, suppose I have m rules, m quadrature point, yeah. So m point rules. Okay, so integral of f is approximate by this rule, yeah. Okay. And so what is the weight? You can see it there. So the weight is, in our case, the weight is just equal the Lagrangian from A to B. Okay? And now what I want to prove is just the degree of precision is at least m minus 1. Yeah? So I take E, so the errors, yeah? So the errors will be x to the k, right? So what is the errors of x to the k? By the definition. You see it? You can see it, right? So the errors will be integral of, so remember the errors is defined to be the integral of exact function okay, minus the quadrature. So minus the quadrature here. So this is the exact function, yeah? And the quadrature will be sum of the weight, and the function will be xi to the k, I from 1 to m. So here k is some number less than or equal m minus 1, okay? Because what I want to prove is only for degree less than m equal minus 1, yeah? So then, so this one will be, by definition, this one is just integral of Li x dx from a to b, right? And this one is just xi to the k, and I from 1 to m. Yeah? And now I can redistribute it. So now, you know, I mean, this one I can change the sum and the integral. So this one look like the sum I from 1 to m, Li x, xi k, dx. Yeah, I just switch the sum and the integral. Right? So I just definition, I just plug into the definition. And now I combine everything underneath the integral sign. So I have AB, have xk minus sum of Lix, xi to the k, I from 1 to m, dx. Right? And now I claim that this one equals 0. The integrand equals 0. Why is that? So now I claim that this one equals 0. The integrand equals 0. So why is that? Yeah, so you see this one on the right, you know, so if I label this one to be pk, yeah, so this one is my pk, yeah, so this one is pk. X equals sum of Lix, xi k, I from 1 to m. Yeah? Then by definition of the Laurent interpolation, so pk, you know, just interpolate x to the k, right? Okay, because remember the formula for Laurent interpolation, you just have sum of f xi times Lix. Or you can verify directly. So pk, when you plug in xi, it will equal xi to the k. Yeah? And so, you know, because k less than or equal m minus 1, so this pk has to be identical to x to the k. Yeah? So because, you know, degree of the polynomial pk is less than or equal, equal k, yeah? So it is just equal k, yeah? Okay, less than m minus 1. So x to the k, degree k is just equal k as well, and less than or equal m minus 1. So they have to be identical. So pk identical x to the k. Okay, because remember you have m minus 1 points, but you have degree k. Sorry, you have degree m minus 1, but you have m points. Yeah. Okay? So therefore, the integral just equals 0. So the integral just equals 0. So the errors of xk just equals 0 for k from 0 to m minus 1. Yeah? So, I mean, if you put in m points and the degree is m minus 1, yeah, then, I mean, it has to be the same, yeah. So therefore, the errors of x to the k just equals 0. So we prove this. So the degree of precision will be at least m minus 1, yeah. And now, so the next part is what happens if I take k equal m. Finish this one, yeah. So now the next step is what happens when I put k equal m. So I put e equal x to the m, then I have the same thing here. So I have ab x to the m minus I from 1 to m lix xi to the m dx. Okay. And now, what can I claim about this? So you see that now suppose I have, say, like m equal 2, right? And then you have like x squared minus sum of lix from 1 to 2 xi squared, right? Then you see you have only 2 points, yeah? But it's a quadratic, so there's infinitely many quadratic that go through 2 points. So you cannot claim that, this one equals 0 anymore. Yeah? So before, when you have something less than m, then it's okay, because the number of points, is more than the degree polynomials. But now the degree polynomials is the same as the number of points. Yeah, so you have infinite many parabola that go to 2 points. Okay, so now how do we say that? So here we cannot say that equals 0, right? But now we have to use the second assumption. The second assumption is m is odd and the points are symmetric with respect to the midpoint of the intervals. So we haven't used this assumption. Okay? So if m is odd, so then this case is not correct, yeah? So this one is m is even. Okay? But suppose m is odd, so suppose m is 3. Then you have, say x cubed minus sum of I from 1 to 3 lix xi cubed. So you have 3 points. Yeah? So symmetric with respect to the midpoint. Yeah? So that like AB and A plus B over 2 here. And then, now still for 3 points, you still have infinitely many cubic that go to 3 points. Yeah? So we cannot say that this one equals 0 easily. Okay? So that might not be equal to 0. But now if you remember interpolation, so if you remember back in the interpolation chapter, so this one still might not be equal to 0, okay? Yeah? But now if you remember back in the interpolation, in topic 4 interpolation, yeah? So we have a theorem that gives you the difference between the polynomials and the, yeah. So the errors, yeah. So if you look at this theorem, so it gives you the difference between the polynomials and the function. Okay. So in this case, what is the function? So in this case, then f is x to the m, right? And p, so what is p? So p will be the sum of Lix, xi to the m, I from 1 to m, right? And now the difference, so f minus p, so f minus p, okay, what is just xm minus sum of Lix, xi to the m, I from 1 to m, can be written as this expression. Okay. So now, so it will be written as f to the m plus 1 derivative of some point xi over m plus 1 factorial. Yeah, because degree is m. Okay, and you have x minus x1 up to x minus xm plus 1. Yeah? No, actually we have only m, so we have only m point, yeah? So we have only m points. So now, what is the derivative? So derivative will be, so f prime will be m so f prime is just m x to the m minus 1, yeah? And f double prime is just m minus 1 x to the m minus 2, right? And so on. So f to the m derivative will be just m times m minus 1 up to 1, yeah, down to 1, and x to the 0, where it just so actually this one should be only m, not m plus 1, because in the theorem we have m plus 1 point, yeah. So this one should be only derivative m. Okay, so x to the 0, so this one is 1, so this one equal m factorial. Okay, so we have m to the derivative m is just m factorials. Okay, so this one give you, just m factorial over m factorials x minus x1 x dot 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 x minus xm. Okay, because in the theorem we have m plus 1 points, but here we have m points only, yeah. So that's why we have to adjust the number of points here. Okay. So what is the result? So the result is, so f minus p is x to the m minus sum of Li x to the m I from 1 to m. It just equal m factorial over m factorials, where it's just 1, yeah. So I just make it 1, and x minus x1, x minus x2, and so on, x minus xm, yeah. So it's a non-zero function. Okay. However, whatever. It has some special structure. Right? So it's just a product of x minus on the factorials. I mean on the interpolation point. Yeah. So now what I want is I want to evaluate what is e of f minus p, right? Because this is what we are doing. So sorry, we want to evaluate e of x to the m. So that's what we are doing, yeah? So e x to the m, yeah? So, and it will be, it just equal the integral of f minus p from a to b. And what is just the integral of x minus x1 dot x minus xm dx from a to b. Yeah? And now we have to use the assumption that, so now, you know, we go back to this theorem. We have to use assumption that m is odd and the point is symmetric with respect to the midpoint. So suppose m is odd. So now take the case when m equals 3 again. Yeah? So you have, you know, so like suppose x1 is here, x2 is here, x3 is here. Okay? Then, you know, this one will be an odd function around x2. So you will see that. So because, so this one will be integral of x minus x1, x minus x2, x minus x3. Okay, from x1 to x3. Yeah, and you will see that is an odd function that behaves like this. Yeah, so it's zero at x1, x2, x3. And it's symmetric with respect to x2. And it's an odd function. So the integral will be 0. Yeah? So therefore the integral equals 0. So in general, you know, you can do a transformation, you know, to make this one is an odd function around the midpoint. Okay? So in general, you can show that, you know, x minus x1 up to x minus xm is odd when you transform the origin to the midpoint. And hence the integral equals 0. Right? Because, you know, you introduce a linear transformation to shift the origin to the midpoint. Yeah? And it becomes an odd function. And integral of an odd function around, you know, the symmetric region will equal 0. Yeah? So that is the idea of the proof. Okay? Yeah? So it can be done formally, but roughly speaking, that is the idea. So you just transform it, the origin to the midpoint, and when you transform that, the integral doesn't change, right? But then it's become an odd function, symmetric over the origin, integral just equals 0. So that's why we have this theorem. So the proof was written in the lecture notes already, guys. So just need to understand, but it's there in the lecture notes. Yeah. So any question about this one? So that is the general results for degree of precision when you have a m-point quadrature, right? M-point Newton-Cotes quadrature. And so now we go a bit further into the errors. So the errors. So before, like we just talked about degree precision, so it's like when the errors equal 0, yeah? But in general, the errors cannot be equal 0 for a general function, right? And then, so there is a theorem. So this theorem actually just comes from Taylor expansion. But first, I just state the theorem first, and I show you where we get it from, yeah? So here is the theorem. So suppose you have the errors is given by the exact integrals minus the quadrature, okay? Then the errors can be written in this form, yeah? So the errors can be written as the integral of some special function. We call it a piano kernel. So named after the first person who recognized it. Integral against the derivative of the function, but order r plus 1. So remember, r is the degree of precision. Okay? So see, in general, I mean, you can express the errors in this form. And k is named kernel, the piano kernel. So the k is defined like this. So k is just the errors of this function phi t. Okay? And the phi t is defined from this. So it will be a function of two variables. Well, actually, t is a parameter. So you can say that t is a fixed parameter. So you have x minus t to the power r. So subscript plus means that it will be 0 if the x is less than t. Okay. So roughly, where do we get this theorem? So now, if you look at the definition of the error function, so you look at the definition of the error function, yeah? Quadrature of f, okay? So now, before we do this, we split f into a polynomials, p, plus some higher order term, right? So something like higher order. Okay? Then, so maybe label it q, yeah? So maybe like, so this one is like p plus q. So p now is of degree r, so degree of p just equal r, okay? So you can do that. Remember, you can do that by Taylor expansion, right? So Taylor expansion, you just have this one is a Taylor polynomial of degree r, and this one is just a remainder, yeah? So then E of f will be the integral of p plus q minus, well, q is not a good notation, because we use q for the quadrature already. So what did I use in lecture notes? Maybe r, yeah. So r is a better notation, r, yeah. Because we use q here already, yeah. So r for remainder. Okay, so minus the quadrature applied to p plus r. Yeah? Okay. And now, so you can split this one into integral of p minus the quadrature of p plus the integral of r minus the quadrature of r. Yeah? And so this one, remember, because p is a polynomial of degree r. So then the integral of p will equal the quadrature applied to p. So this one equals 0. Okay? And now what you have left is just this integral of r minus the quadrature of r. Okay? And now, so now if you write down explicitly, this one just an integral of r, yeah, from a to b, dx minus the sum of r xi, the weights, I from 1 to m. Yeah? Okay? And now, you see, now depends on how you choose the r. Okay? Then you have some special form of this expression. And that is the piano kernel. So that is the idea of the proof. So the original, so now go to the proof and I will show you. So now if I open the lecture notes. So this is the proof of the previous theorem, yeah. So I just explained it, but it was written here in the lecture notes, yeah. So now the error is here. Okay, so R here. So first you write F as P plus R. Okay. And so P is Taylor polynomials, and the remainder. So actually, if you look at the Taylor polynomials, there's two forms of remainder. One was given as the derivatives, okay, and another form is given as integrals. So there's two remainders formulas for Taylor expansion. So this one we use the second one, the integral version. See, so you can see that R is given as the integral version. Okay, so will be given by this integral. And now, so like I said, so now the errors of F is just the error of R. And if you plug in this special remainder for R, then you can reduce, the errors. So this one is the integral of R, and because it's a double integrals, yeah, because you have the remainder in terms of integrals, and you have the integrals of R, so it's a double integrals. And you can change the variables a little bit, so instead of dt dx, you can change it to dx dt, yeah, by Fubini theorems, okay? And then you plug it in. Then you have, this one is just a piano kernels. Okay, so piano kernel is just this. So so this one can be rewrite as a piano kernel. So this one, the Holton, yeah, the Holton here can be rewrite as a piano kernel. So by choosing the integral form of the remainder. Okay, so then you can rewrite this. And so we are going to give some example of piano kernel. So suppose you have, you see, so in the end, then piano kernel is just given by this formula. Okay, so it just come from here, from the definition. And piano is just the first one who write down explicitly, and we got a name for that. So you can write down some formula, and 200 years later, somebody will go after your name, So now we will take some example. So suppose you take trapezoidal rules. Okay, so now what is a piano kernel for trapezoidal rules? So see, so this one is just another way to write piano kernels. Yeah, so you write in terms of this errors of this function phi t, and you saw it before, but I mean it's more or less the piano kernel is just this one, the integral of. So where does this come from? It just comes from the remainder of the Taylor expansion, okay, in integral form. Yeah, so you just integrate the remainder minus the quadrature of the remainder. That's it. Okay, and the remainder of Taylor expansion is given either, could be given in this integral form. Yeah. So now, example. So how do we find out the piano kernel for trapezoidal rules? So remember, what is the trapezoidal rules? So trapezoidal rule is trapezoidal rules look like this. Yeah. So you have, again, everything is just one interval. So you have trapezoidal rules look like this. So FA here, FB here. So trapezoidal rules is just 1/2 FA plus FB B minus A. Okay? And now I want to find out what is the piano kernel for this quadrature. So I go back to this formula, the general formula. Okay? Then KT, okay, is given by the integral from t to b of x minus t to the r. So what is the degree precision of the trapezoidal rules? 1, yeah? So trapezoidal rule degree precision is just 1. Yeah? And you can look at this way. So degree precision is, what polynomials that it can integrate exactly. So, if you have polynomial degree 0, it will integrate exactly, right? Degree 1, integrate exactly. Yeah, it's a linear function. But if it's quadratic, then this no longer exact, right? So if it's a quadratic, you cannot approximate the area by the area of the trapezium. Yeah, so you have, so from that, that degree precision of trapezoidal rules is just 1. Okay, so now back to the piano kernel. So now, if I plug it in this formula, yeah, so r just equal 1 over 1 factorial. Okay, then dx minus the sum of, so minus the sum of, now say that xj bigger than t, yeah? So xj bigger than t, wj xj minus t over r is 1 over 1. Yeah? But so now, what does it mean by xj and wj? So remember, you have a quadrature, is 2 quadrature point is x1 equal a, yeah? So x1 equal a. Okay, so x1 is just the first quadrature point, and x2 is just equal b. Yeah, and the weight is just equal, b minus a over 2. Yeah. So now what we are looking at, we just take xj bigger than t. So where is t? T is between a and b. Yeah. So t is between a and b, yeah? So t here is between a and b. So then what quadrature is always bigger than t? So you have only the second point, right? Only when you have j equal 2, then x2 will be bigger than t. Yeah? So then you have this one will reduce to you just have the weight is b minus a over 2, and this one is just b minus t. Yeah? Because you have only one point bigger than t. Okay? And so now this one become, after you plug it in the formula, this one becomes a simple calculation. So this one gives you x minus t square over 2 and x equal t, then x equal b minus b minus a over 2 b minus t. Right? Yeah? And that is, so now if you put in x equal b, you have b minus t square over 2, and you put x equal t, you just got 0. So b minus a over 2 b minus t. So you got b minus t over 2 is a common factor, and you have b minus t minus b minus a. Okay, so this one just b minus t over 2, then b minus b here, so you got a minus t. Okay, so as long as you plug in the formula correctly, and the rest is just some calculation of integrals. So that's what we have here. So b minus t, and then a minus t. Yeah. So a minus t. So here 1/2 minus 1/2. So just that is how you got the piano corner. Okay. So just the tricky part is how you plug it in the formula correctly. So okay, and then after that everything is. It's just the direct calculation. Yeah. So you can try the piano kernel for midpoint rules. Okay, so midpoint rules can be computed, and it should be given like this. So eventually, after a long calculation, you can get out this formula. Okay, and actually I think I did this calculation in the lecture notes. Yeah, so if you look at the lecture notes, here, yeah, so now, so for midpoint rules, you can see that if t is between a and 1/2 of t, then the kernel can be expanded like this. Okay, and if t is between a, the midpoint, and b, then k is written like this. So we can go through this a bit more details in the tutorials. Okay, but that is how we get out the formula. So maybe we take, say, 10 minutes break or 5 minutes break. So how long do you want to take? 10 minutes break, yeah. So we start again at 11:04, yeah. And the and one more thing, the lab is due. I mean, the project is due at the lab in week 10. But I realized that your last lab in week 10 is going to be at that day. I mean, if your lab is on Thursday, so I'm talking with the office, to have to move maybe to the week after. So, but then how about the week not have the lab on Wednesday? Because Wednesday is not an exact day, right? This means that I have to give some extension to the lab on Wednesday as well. Questions?
On our timetable in the lab for week 11, what did you change recently?
Huh?
On our timetable, the lab changed recently to week 11. Is this lab week 11 now?
You mean the exact day already?
Yeah, it's happened already, I think, yeah.
Already changed and that's a week after?
Yeah.
Okay.
My question is, what if you're in different labs with people in your group?
You can choose either one. You can choose either lab to work. I mean, you have. So actually, we have 3 groups. One is in lab on Wednesday, and 2 on Thursday. Okay. So you can choose either. But you see now, because the lab on Thursday has been extended for 1 week, so that means that the group on Wednesday should be extended as well. Right? Otherwise, not fair, right? So then maybe I have to talk to the office to move the lab on Wednesday to the group. I mean to the week. After Anzac Day as well.
Is chapter 7 the last?
So the project is about chapter 7. Okay, just for you to study chapter 7. Okay, so the project is not hard. As long as you study chapter 7, then you can do it within like 1 or 2 hours. Yeah?
And chapter 7 is what? The next one is after this.
Huh?
And the chapter 7 that's after this topic, right?
The last one, yeah?
Yeah, so this is topic on 6, right?
Yeah. So we have only one more topic because now we're on week 7 already. And remember, you have only 10 weeks. Yeah, so 8, 9, 10.
Yes.
Okay? Yeah.
Applying that 4,500 integrals.
Yeah.
Plugged in at the end b minus t.
Yeah.
Because x has to be greater than t, and you know that t is
less than b.
Yeah, t is less than b.
Yeah.
So t is greater than p.
Well, because t is moving only between a and b. So actually t is strictly less than b.
Yeah.
Yeah, so actually t should be strictly less than b, yeah. Because we integral, remember t is the parameter here, so it moving between only a and b. It's strictly less than b.
So every time we just always going to plug in the upper.
No, it depends. No, it depends. So maybe that's why we should discuss the other example. For another example, you don't have that case anymore. So we discussed the midpoint rules. I think I will discuss the midpoint rules. Yeah, that will be slightly different. Yeah. You mean on week 11?
So
Yeah,
you
you can do
yeah.
week 11. Yeah, it's up to you. Yeah, because week 11 is not Anzac. Sorry, Wednesday week 10 is not Anzac day.
Could do it.
You could do it that. Okay. So but then only the other lab is moved. Yeah. Okay. And then what happened to the tutorial on Monday? Anyone know? So, because Monday we have Easter Monday as well. And then anyone has a tutorial on Monday? Yeah, so what does it say on your timetable? To Tuesday. So with Monday then move to
Monday and Thursday tutorial. And I think that one on the Tuesday. Everyone. I think.
Otherwise, you can go to different tutorial, because we have 3 tutorial groups. Yeah, so one on Thursday, one Monday, one Thursday, one Friday. Yeah, so maybe, because it's a week, you can go to other tutorials. Okay? Okay, that's fine. Okay, so maybe we talk a little bit about the piano kernel from midpoint rule because it's slightly different from this. So suppose, I want to find out the piano kernel from midpoint rules. So remember, what is a midpoint? So the midpoint rules look like this. So you have only one intervals, yeah? And your function look like this. And you just take the midpoint. So this one is A, B. Okay, sorry, yeah. Okay, so the midpoint rule is just, f at a plus b over 2 times b minus a. Okay, so this is the midpoint rule. So just take the value at the midpoint and you multiply by the width of the intervals. So what is a piano kernel in this case? So degree precision, remember degree precision is 1. Yeah? So now the piano kernel look like this. So integral from t to b x minus t to the 1 over 1 factorial still 1. So dx minus sum of the quadrature point bigger than t, the weight xj minus t to the 1 over 1 factorial. Okay? And now you have only one quadrature point. So x1 will be just a plus b over 2. Yeah? Now the problem is T is moving. T is moving between A and B. And now the quadrature is right in the middle point. Yeah? So you have to split into two cases. Yeah? Now you have to say that, okay, what happened when T is less than the midpoint? So what happened when T is less than the midpoint? Yeah? Because you know, T is moving, but now we have to divide it into two cases. So what happens if T is less than the midpoint? Then then the errors, so then the KT, that the piano kernel will be, you know, so you still integral from T to B x minus T dx. But now, what quadrature point is bigger than T? Well, definitely, you know, the quadrature point, we have only 1 point, yeah? But then you have A plus B over 2 is the quadrature point, it's bigger than T, only one point. So then you have the weight, so the weight is B minus A, and the quadrature point is A plus B over 2 minus T, yeah? And then this one you integral, and this one should give you like x minus T square over 2 x equal T x equal B minus B minus A. And this one is A plus B minus 2T over 2, right? And now so you plug it in, you got B minus T square over 2 and T minus T just equals 0, so B minus A plus B minus 2T over 2, right? And now then you have to do some simplification. So suppose I have like 1/2 is the common term, right? So 1/2, then I have like B square plus T square minus 2BT, and this one will be BA B square, so BA B square and plus 2BT, yeah, and then minus, well, minus become plus A square, so plus AB and minus 2AT. Okay, something like that, yeah. And you can cancel. So cancel B square here, B square here, AB here, BT here. So in the end of the day, you just have only 1/2 T square minus, oh sorry. So you have only T square plus A square minus 2AT. Yeah? And that is 1/2 A minus T square. Yeah? So just some calculation. Okay? So that is exactly what I have here in the lecture notes. In the lecture note, I just didn't do the middle step, but I got the same answer here. Okay, 1/2 T minus A squared. And then now you consider the second case when t is bigger than, so you consider the case when t is bigger than a plus b over 2 less than b, yeah, less than or equal b. Then now kt will be integral t to the b x minus t dx. But now there is no quadrature point bigger than t, yeah. See, now t is bigger than the quadrature already, so no more quadrature point. So you just put in 0 here, yeah. And then this one gives you x minus t square over 2 x equal t and x equal b. So just equal b minus t square over 2. So in this case, then kt equal 1/2 a minus t square for t less than a plus b over 2. Yeah, and 1/2 b minus t square for t bigger or equal a plus b over 2 less than equal b. Okay, so that is the case we have here. So that is the calculation for the midpoint rules. And I think in the slide, this one should be strictly less than, yeah? Strictly less than in the slide. And this one less or equal. I will fix the slide, okay? The slide, I think slightly not correct. It should be strictly less than, yeah? Then you have this. Okay? And now, question?
So what did you mention? T is moving.
T is a parameter. So now if you go back to the formula, yeah? So T here, okay? So T here is the variable inside this integral. And you integrate from a to b. So the range of t is between a and b. Yeah? Because we have two variables, x and t. Yeah? So x is your variable for the function, but t is just the variable for this integral. Yeah? And and look at this one. Actually, you can show that, you know, if k doesn't change the sign, then there exists a constant, so that the error is just equal, you know, the integral of kt multiplied with some point c, so that you take the derivative of order r plus 1. So this one, you know, it just, they call it the mean value theorem for integrals. Yeah, so mean value theorem for integrals. So essentially you can take out this f to the derivative order r plus 1 outside, yeah, at some point c in the interval a and b. Okay, so this one just comes from the mean value theorem for integrals. Okay, so there's the mean value theorem for integral. But the idea is essentially you can compute the errors of f by, you know, integral of the piano kernel multiplied by the value of derivative of the function, you know, derivative order r plus 1 at some point. Yeah, so that's the consequence. So now, you go back to this. So for midpoint rules, then you have this formula. So remember, for the midpoint rules, for midpoint. So we compute we just compute the midpoint rules. The midpoint rules here, we just compute this. And we know that the errors will be given by, so errors of f will be given by integral of kt from a to b, then the derivative of the second order, because the degree precision is 1. So that's why you have second derivative here. Okay? And this integral, so now you have kt here, so you can integral kt, so this integral is 1/2 a minus t square from a to a plus b over 2 dt, so this integral with respect to dt, and integral of 1/2 b minus t square for a plus b over 2 to b dt. So you see, this formula allows you to give the errors very precisely. So it's an integral of the Peano kernel and multiply by the derivative of the function f, second derivative at some point. So c is between a and b. Okay? And if you do this calculation correctly, so this one is like 1/2, then a minus t cubed over 3 from a to a plus b over 2. And this one is 1/2 b minus t cubed over 3 a plus b over 2b. So if you do the calculation correctly, you should get b minus a cubed over 24. Okay? So there is some calculation to plug it in correctly. So if you plug it in correctly, then this one should simplify to be, so there's some middle step here, so well, we can plug it in. So now suppose I plug it in, then you have a minus a plus b over 2. So you have 1 over 6 here, cubed, right? Then when you plug in t equal a, then it's equal 0. And here you have 1 over 6 as well, and you plug in b, and it's equal 0, so you got, so it's become a b minus b, a plus b over 2 cubed. And see now, because if I plug in b here, I got 0, so I have to plug in a plus b over 2, So, so the first one I should get like 1 over 6, and this one is a minus b, no, should be b minus a, No, a minus b is correct,
The second term should be b minus.
b minus, so b minus.
Shouldn't it be like negative whatever that is? We can't see it.
Sorry, which one?
Yeah, that thing you're pointing at, we just can't see it. I think.
You mean like this one?
Should that maybe be negative whatever it is?
What's negative? Sorry.
The b minus b is a positive. And oh, I see. You took the minus sign. Okay. Sorry.
Yeah. So should be a bit here. So because because the when I plug in t equal b, it's equal 0, then I minus, so there should be a minus here. So I have to plug in t equal a plus b over 2. Okay. Okay, I forgot. Okay, so there should be a minus on the inside. So there should be the same here. Should be here as well, right? Should be a minus here as well. And minus here as well. Okay, so then there should be a minus here and a plus here. Okay, so we have minus here and plus. So this one is like b over b minus a over 2 over 6, yeah? So then essentially you will have twice of, so 2 to the, so 48, yeah? Then b minus a cubed, which is 1 over 24 b minus a cubed. Okay? Yeah, so we got it correctly, yeah? So there's some calculation, but it's not difficult, yeah, just a bit tedious. So to show you that, you know, you can derive the errors in some very concrete formula. Yeah, so that the midpoint rules, the errors, it just equal b minus a cubed over 24 second derivative of f, yeah. And you can do the same for trapezoidal rules. So trapezoidal rules, by, you know, evaluate the integral for piano kernel, you can get out this result, okay? B minus a cubed over 12 and minus then the second derivative. So now Simpson rules, you can do the same as well. It's a bit complicated, you know, I mean, just plug in maple and then you can get out the Simpson, for the Simpson rules, the piano kernel is given like this. And the error is given like this. Okay? And so this one is b minus a to the 5th. And the piano kernel, I mean, even it looks two pieces like this, but actually it's continuous. You can check that when you plug it in t equal a plus b over 2, you get two values are the same at the joints, yeah? Okay, so this is the plot of the piano kernel. So now we move on to composite rule. So it's like you just divide it, you know, like the Riemann sum, you divide it into n intervals. Okay? Then what is the errors? So now, so you know, you divide it into n intervals by put in n plus 1 point like this, and then hj is just the width between the points. Okay. We also define, you know, the point in the middle of xj and xj minus 1. Okay, to be xj minus 1/2. So this one we just define it. And now the midpoint rules. Okay, when you define like this, give you this formula. So let me draw a picture. So we have A and B. Okay, so A and B like this, yeah? And you have, so this one is x0, and you have x1 and x2 and so on. So this one, the last one will be xn. Yeah? And then this one, the h1, so h1 will be this one, the width between, you know, x1 minus x0, and this one will be h2 and so on. Yeah? And then you have xj minus 1/2. So this one will be your x 1/2. Okay, and this one will be your x 3/2, and so on. Yeah. And now the midpoint rules. Okay, so now you have many intervals like this. Okay, so the last interval look like this, yeah. And you take the midpoint. So the midpoint is here, yeah. So the first area will be x 1/2. I mean the weights the value of x 1/2 times the width of the first interval, so h1, and plus the second one, so x 3/2 times h2, and so on. Yeah, because the midpoint, remember we take the value of the midpoint. Okay. Then you have this formula. So it will be the sum of xj, fxj minus 1/2. Okay, so j equal 1, then you got h1 and x 1/2 here, j equal 2, you got h2, x 3/2 here, and so on. Yeah. And if I want to make life simple, then I just use a uniform partition. So if I use a uniform partition, then the step size are the same. Yeah, so the hj equal the same, h. And then if it's the same, you can pull it out. Then you have this sum. So sum of f xj minus 1/2. Yeah. So this one is the sum of f xj minus 1/2 hj, j from 1 to n. Okay. And now we still have the errors. So the errors will be, the difference between the exact integrals minus the sum, the quadrature sum. Yeah. So now you have the sum of hj, fxj minus 1/2 here, and this one can be decomposed at the errors on each intervals. Yeah, so Ej is the errors on each intervals. And so we are not going to prove this, but because based on the previous results, remember for one interval, you can estimate this. Yeah. So we discussed before, yeah. So now, so if you look at this Ej, so we discussed before that so remember we have Ej here, is just the errors xj minus 1 to xj of f x dx minus hj f xj minus 1/2, yeah. But these errors, so remember if you have only one intervals for the midpoint rules, okay, we have this formula, right? So this formula, when we apply to this case, so remember, you have only, so B and A, so in this case will be xj minus 1, yeah, time, cube, yeah, divided by 24. Yes, that's the midpoint rules. Yeah, so the midpoint rules will be f second derivative. So C is between xj minus 1 and xj. Okay, and this one is just hj over 24 cube f double prime c. Yeah. And then we just sum up all the errors, right? So if we sum up all the errors, then we can show that okay, so we can show that the composite midpoint rules, okay, the errors can be written like this. Okay, so there's some step in proving this, but now let me skip it, and it can be said that it is based on the errors you computed for each subintervals. Okay, you can get out this error estimate. So, but pay attention to the order of h here. So this one h squared, yeah, and here, you know, you have f double prime, yeah. So you have to require the function at least twice differentiable, okay. And the b minus a over 24 come from this calculation, come from the area of each intervals, okay. And now, similarly, you can do the composite trapezoidal rules. So composite trapezoidal rules is now, you know, you have you have x1 here, sorry, x0, x1 up to xn, yeah. And the first one you have a trapezoidal rule here, so the second one maybe this, and the last one is maybe this. Okay, and then you sum up on the area. So the first area will be 1/2 fx0 plus fx1 times h1, and then the second one will be 1/2 fx1 plus fx2 times h2, and so on, yeah. And you can see that you can write this one as a sum of fxj minus 1 plus fxj xj over 2, yeah, like in the slide, yeah? But you know, you can simplify this a bit when all the hj are the same, yeah. So if all the hj are equal h, then you can see that you can take out h here, yeah, and then you have 1/2 fx0, the first one, but the second one, this one add up with this one, so 1/2 fx0 here, 1/2 fx0, so you have full fx1, sorry, 1/2 fx1, 1/2 fx1, and so on. And only the last one, then you have 1/2 xn, okay? And that gives you the composite trapezoidal rules with the same step size. And by splitting the errors into small subintervals, you can show that the errors is of this form, yeah? And now pay attention. So here you have h squared, okay? And you require the derivatives. I mean, the function has two derivatives. At least the second derivative should exist. Otherwise, this doesn't make sense, yeah? And then, if you use Simpson rules, okay? So Simpson rules, remember, we have to consider the midpoint. So there is the midpoint here. So for f, j minus 1/2 here, okay? And then for a uniform step size, you can pull out h, okay? But look at the error. So now the errors is order h to the 4th, but you require 4 derivatives, okay? So then for 3 rules, so which one is give you the smaller errors when you take h small? Simpson rule, right? Because h go to 0, then h to the 4th go to 0 faster than h squared. So Simpson rule is more accurate. And you can see that, but the price you have to pay is you have to require f is 4 times derivative, 4 times differentiable. Otherwise, you might not have this statement. Okay? And those numbers just come from the integrals of the piano kernels. Yeah, so those magic number, 2a0 just come from when you integrate the piano kernels, then you get those numbers. So that's that I said, yes. In terms of the errors, then smooth integrand Simpson rules will be more accurate than the midpoint and trapezoidal rules. Okay, so if you have a C4 function, then you should use Simpson rules. Okay? And so this is the way we implement it in MATLAB. So remember we had this formula before. Simpson rule is just 2/3 midpoint rules plus 1/3 the trapezoidal rules. You can use this formula to apply into this MATLAB, so you can see that. So diff here in MATLAB, it's just the difference. You just take xj minus 1, and it gives you the. So remember in Maple, diff gives you the derivatives, yeah, but here just gives you the difference, yeah. So diff here doesn't give you the derivatives. Question?
Does MATLAB do differentiation theories that or not?
You can use symbolic package, but it's not recommended. Okay, because why? Because symbolic package, more or less, it just load Maple engine into the memory, so it will slow down everything. Okay, so I'm not going to use any symbolic package during this course, but it's available. Okay, you can compute derivatives, symbolically, but it just slow down everything. Yeah. But in this case, it's not derivatives. It's just like the difference. Yeah. So exactly xj minus 1. And then you can define x half like this. So x half is just xj plus h over 2. That's the definition, yeah? And then the midpoint rules is just the sum of, xj times x half. So remember, this is a vector. This is a vector. So that's why you have to have a dot here and a star here. So just take every element and it just take the pointwise product, yeah, and then take a sum. So this one gives you the midpoint rules, sum of hjf of xj minus 1/2. And then the trapezoidal rules. So remember we have the formula here, so it's just exactly here. So half h over 2, then, so this is a vector, start from x1, and this one is, so when you have n minus 1, just take the last index. So you don't have to worry, it could be 100, could be 1000, but it just automatically compute the length of the vector. Okay? And the Simpson rule is just by this formula, so 2 midpoint rules plus the trapezoidal rules, then divided by 3. Yeah? And so we just apply the Simpson rules to compute this table. So in this case, the exact integral of this one, yeah? So what is integral of 1 over x squared? Huh? Inverse tangent, yeah? Arctan, yeah? So arctan of square root 3 just gives you 5 over 3. So you know the exact integrals. And you just put it in, for different number of intervals, okay? Then it gives you different results here. So you can see that for n equal 2, for 2 intervals, then the third digit is not correct for midpoint rules, yeah. But it's correct for Simpson rules already. So Simpson rules can give you the correct digits here, the third digits here. And if you have a lot of intervals, 160 intervals, then so look how many digits does it get. So 1, 2, 3. So 1, 2, 3, 4, 5. So 5 digits for midpoint rules, yeah? 1, 2, 3, 4, 5. Okay? But it's wrong in the 6 digits. But now look at Simpson rules. So it's correct up to 1, 2, 3, 4, 5, 7, 8, 9, 10, 11. So it's pretty good. So you see, up to 11 digits after the dot, Simpson rules, yeah? And you can implement it. So this one is so we look at the errors. So this is the errors. So the errors is like you just take the difference. Okay, the midpoint. So like 10 to the minus 5 here. But this one is 10 to the minus 3, 6, 9, 11. You know, so Simpson rule is better. Okay. So how do we compute the order of conversion? So in general, suppose you have errors like this. Yeah. How do you compute the order of conversion? So I mean numerically, you just know the order of conversion theoretically, right? But how you compute the errors numerically? So numerically, you know, suppose I have. So it will be from this formula. I mean, maybe you have seen it, or maybe you haven't seen it. But let me explain it a bit. Yeah. So suppose you have run the program, and you get a table like this. Yeah. Then how do you compute the order of conversion? So suppose you have H1. So H1 is here, and H2. Yeah, because from n you can derive h, right? So 1 over n is just h, and you have errors here. So error 1 and error 2. Huh? Oh, sorry. No, it should be on, yeah. Anyway, so what I want to say is, suppose you have suppose you have error, you have H1 and H2, right, from the table, and then you have error 1 and then error 2, also from the table, right? And you know that these errors will be something like C H1 to some power alpha, and this one will be C H2 to some power alpha. And what is the power alpha? Well, I mean, you just take H1, right? Sorry, you just take E1 over E2. You just take E1 over E2. So E1 is just from the table, right? Over E2. Then you have H1 alpha over H2 alpha. Right? So then you take the logarithm. So this one is just H1 over H2 to the power alpha. So you take the logarithm, then you have logarithm of any logarithm is okay, yeah? Alpha logarithm of H1 over H2. And then from this you can derive what is alpha. right? So that is the way you can compute.
How is it coming from the table? What's n?
So you see, what is n? So n is the number of subintervals, and h is just 1 over n. Yeah, so h is just 1 over n. So this one is 1 over n1, and this one is like 1 over n2, right? Yeah. So suppose n equal 2, then h1 is just 1/2, and n equal 10. This one just 1 over 10. Yeah. Okay. And suppose you have errors here. So the errors for n equal 2, it's just for suppose it's for midpoint rules, you have 0.0043 or whatever, and this one is 0.00027. So this one, essentially, if you look at the project, the very last question, I asked you to deduce what is order of conversion, just based on the errors you got, not from the theory, just from the type of errors. Then you have to use this method. Okay, just based on the numbers given by your program, you can deduce the order of conversion. Empirically, so just from experiments, not from the theory. Okay, so that is exactly the formula here. So you can derive the order of conversion by just taking the logarithm of the ratio of the errors over the logarithm of ratio of h1 over h2. And if you look in the project description, h1 over h2 is roughly 10. No, actually exactly 10, because I have 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. So then, this logarithm, just logarithm 10. Yeah. So then the order of conversion just gives you of the logarithm of this ratio.
So rho is the order.
Yeah. In this case, is rho is here. Yeah. Should be rho. Yeah. And rho is the order of conversion. Yeah. And now by this, then I can plug it in the table again, and you can see that for midpoint, then I have, the power is 1.3 here, but when I increase the number of subintervals, it gets better and better, so I got 2 here, yeah, and here, I got 2 here, yeah, and here I got 4, you see, so this one is we verify the theory by the numerical experiments. It's like in physics, you do some experiments, you measure something, and you test again the formula. Okay, and then that is exactly the case here. The theory says something, the order of conversion of Simpson should be order 4. Remember the theory, the theorem. And here it should be order 2, h squared, this one should be h squared. H to the 4th, yeah, should give you the correct order. Okay. So, any question about this before we might have time for Gaussian rule? I don't know. 5 more minutes. Any question from this table? Question? Yeah.
Just regarding the quadrature. Just when you said that, I think it was the Peano kernel for what was the one that was split? Midpoint rule.
Midpoint rules, yeah.
Said that when t is between b and a plus b and 2.
Yeah.
I was wondering why isn't there a quadrature anymore? Isn't that because there's no more quadrature points left? But I'm not really sure what you mean.
You mean this one for the second point? Well, because the formula. So if you look at this formula, yeah. So this is a Peano kernel, yeah. So remember if so it's a bit. So we go back to the calculation. So you have kt, right? Is t to b, and x minus t, because r is 1, so you don't have anything here. And then xj bigger than t, xj minus t, and wj, yeah? So now the case when t is bigger than a plus b over 2, right? Then, so you can see that, I mean, now the quadrature, so you have only one point. The quadrature here, only the midpoint, yeah? So x1 is actually a plus b over 2, right? So t is here, so t is here. Yeah? So now, if t is here, then there's no more quadrature bigger than t. Because the quadrature, we have only one quadrature. Yeah, so the quadrature is a plus b over 2. So, and t is bigger than that, so t is here. So nothing satisfies this condition. I mean, no quadrature satisfies this condition. Yeah, so the midpoint rules is, you know, you have only one quadrature point. And that quadrature point is the midpoint. Yeah. So you see, the quadrature in this case is just f of a plus b over 2, yeah, times b minus a. So this one is the quadrature point, x1, and this is the weights. Nothing, yes. Nothing satisfies this.
Just like for any rule.
Yeah.
T is larger than the quadrature, no quadrature.
Yeah. But see, it depends on how you define the quadrature, huh?
Yeah, it depends.
Yeah, so that's why different quadrature you have different cases. Yeah, so this formula is only for a very general case. When you have any quadrature xj, wj, and the order is r. Okay? So is it clear now? So any other question or? So maybe we can go for the Gaussian quadrature next time, yeah? So see you next week or in the tutorial if you have tutorial.
Leave the truth, let him use something. Like the next.
Yeah. Okay.